Introduction. Energy presence in the form of pressure, velocity, and elevations in fluid with no energy exchange due to viscous dissipation, heat transfer, or shaft work. The relationship among these three forms of energy was first stated by Daniel Bernoulli, who first writes this principle in a book named Hydrodynamics, based upon the conservation of energy principles. Bernoulli's theorem pertaining to a flow streamline is based on three assumptions, which is steady flow, incompressible fluid, and no losses from the fluid friction. Bernoulli's principles state that in a steady flowing fluid, the sum of all the mathematical energies, including kinetic energy, dynamic heat, fluid pressure, and potential energy, should remain the same at all points of the flow. So if any type of energy increase, like if any kinetic energy increase, then the other type of energy, like potential energy, pressure, will decrease to make the final sum same as before. Bernoulli's theorem provides a mathematical means to understanding the mechanics of fluid. It has many real-world applications, ranging from understanding aerodynamics from an airplane, calculating wind load on buildings, designing water supply and sewer networks, measuring flow using devices such as weirs, partial flumes and venturimeters, and estimating seepage through soil, etc. Although the expression for Bernoulli's theorem is simple, the principle involved in the equations plays vital roles in the technological advancement designed to improve the quality of human life. The validity of Bernoulli's equation will be examined in this experiment.
In Bernoulli's principle, it states that as a fluid passes through a system of pipes, when the pressure drops, the velocity increases. So as an example, I have this pipe. So when I open this pipe, the water flows normally. But as I apply a pressure, the internal pressure decreases, causing the water velocity to increase, thus forming a high velocity fluid.
I am Ibemi Sherlimui. I will present the apparatus used for the design and how to set up the apparatus. The apparatus are bottle, straws and tube, scissors and cutter, hot glue gun, soldering iron, and ABS solvent. Next is the procedure in setting up the apparatus. First, cut up the cylindrical bottle to make 3 different diameters of pipe. Each diameter were measured and recorded. Then, about 5 cm of the top part of the small bottle was cut. This part acts as a constricted section of the design. Mark the diameter of the small bottle at the bottom part of another large bottle. Then cut the bottle according to the mark so that the small bottle fit into the large bottle. The bottles were then glued together with hot glue gun and let dry. This step was repeated to get another similar design as the previous bottle. Next, make a hole on the tube using soldering iron to fit the straw at the hole. Glue all the parts to get 3 models with different diameter. This is the 3 different design of parameters. To conduct the test, 4 liters of water was poured into the model. The time for the water to reach a steady state was recorded. The height difference was recorded when the water is in a steady state. The process is repeated for the second model and the third model.
So these are some formulas that we use in this experiment. First, we calculate the flow rate. Flow rate is equal to volume over time in the unit of meter cube per second. Then we calculate the velocity. Velocity is equal to flow rate over area in the unit of meter per second. Then we calculate the velocity head. Velocity head is equal to velocity squared over 2 times gravity in the unit of meter. After that, we calculate the total head. Total head is equal to h plus velocity head in the unit of meter.
Assalamualaikum, my name is Anis Nabila and I'm going to explain about the result and the calculation in this experiment. So for the first pipe, the flow rate is 1.515 times 10 to the power of negative 4, and for the velocity of pipe 1 is 0.3086 meter per second, and velocity head for the pipe 1 is 4.854 times 10 to the power of negative 3, and then the total head for the pipe 1 is 1.585 times 10 to the power of negative 2. For the pipe 2, flow rate is 1.465 times 10 to the power of negative 4. Velocity for the pipe 2 is 0.1523 meter per second. Velocity head for the pipe 2 is 1.182 times 10 to the power of negative 3, and total head for the pipe 2 is 9.182 times 10 to the power of negative 3. Lastly, for the pipe 3, flow rate for the pipe 3 is 1.214 times 10 to the power of negative 4. Velocity for the pipe 3 is 0.0763 meter per second. Velocity head for pipe 3, 2.927 times 10 to the power of negative 4, and lastly the total head for the pipe 3, 2.297 times 10 to the power of negative 3.
In this experiment, we had demonstrated Bernoulli's principle, and referring to the results, gathered further proof that the diameter of a cross-section pipe will affect the velocity and the pressure of the liquid. Smaller diameter of a cross-section pipe will induce a higher velocity of the fluid, while the pressure will reduce. The height of the water in the middle section is lower compared to water flow at the end of the pipe. Larger diameter of the cross-section pipe will cause the fluid to have lower velocity with higher pressure. The height of the water in the middle section is at the same level as the height at the end of the pipe. The pipe with the same size throughout the pipe system is observed to have lower height of water when compared to height of water at the end of the pipe. This shows that there are changes in velocity and pressure which causes the water level to fluctuate. Errors exist in this experiment that causes the height of water in larger pipe to be the same level as stated by Bernoulli'S principle, where the water level should be much higher compared to height of water at the end of the pipe. This is due to the fluid is not ideal as tap water is used. Friction losses also exist in the water particles and the materials used as the model. There are no markings that indicates the difference in water level, in which may affect the observation. To resolve this problem of the fluid is not possible, as ideal fluid is difficult to be produced. Next solution is the friction loss. The friction loss can be solved by reducing the length of the pipe, as fluid will reduce in pressure when it flows to a longer pipe. A ruler is recommended to fix the issue of the marking, as we can identify the height level with precision.